All right, so practice problem has the same setup as last time, and I'm just going to redraw in everything I've done so far. So starting with the solvent point. And so cross current, I think you'll find counter current design problems are actually paradoxically a little bit easier to solve because there's not nearly as much calculation that has to go on in the interim. In other words, in cross current, I had to find physically where the mixing point was every time. For counter current, I just know that the delta point is in the same place every time, so I don't have to spend time calculating stuff if the problem doesn't ask me to do so. All right, Rn is down here. So I want to stage step until I reach Rn down here. I need to know where the overall mixing point is. I need to know where the overall mixing point is because that's how I found where E1 was. So I was again at 67% vinyl acetate. And a line from E1 to the mixing point all the way through to the other side tells me where E1 is. Over there. Now graphically, I have to find where the delta point is. So I draw a line from F to E1 all the way through, and from Rn to S all the way through. Let's see if I size this appropriately. Perfect. Just got it on the page. Delta is over here. All right, as I said, I can go through graphically now. So I know that E1 and Rn are connected by a tie line. So sketching it until it makes it look like it belongs. R1 is there. R1, delta, E2 are on the same line. I'm making hand motions. I've just now realized that you can't see my hand motions. Disappointed in myself that it took that long. Oh well, hopefully it's still clear anyway. E2 on the phase envelope. E2, R2 connected with a tie line. Now my composition of R2 is still, what is it, 14% acetic acid. Therefore, I know I'm going to need another stage. So maybe zoom in a little bit because we're getting intricate. Let's wait for my tablet to catch up. Okay, line from delta to R2, and where that crosses the equilibrium curve is E3. Now I need another tie line from E3 to R3. It looks like I'm still improving, but it's going to need another stage or two. R3 is there. Now R3 to delta. There, and I think this one is going to get me there. So if I sketch in where E4 is, E4 is there, delta, I'm sorry, the tie line now goes across. Where is it? There is it. There it is. And we're pretty close to our 5% specification. So this Rn, oops, instead of drawing it there, I'm just going to draw where n is equal to 4 stages. So just from a conceptual point of view, if I were doing this cross-currently, I would certainly expect less than 4 stages. I don't think I've given you a problem yet that requires more than 4 stages to solve cross-currently. However, for a counter-current, I have more stages. But remember, counter-current uses less solvent, and as a result, in every separation that we've done so far, less solvent correlates to more stages. And the same idea is true here. If I have less solvent, more stages, more solvent, less stages. So think about the other couple of separation techniques that we've used. If I'm comparing, if I have the option to go a low amount of solvent for more stages, or if I can do more solvent with less stages, which one is more economical? So I have this trade-off between stages and solvent. And if I say it in a slightly different way, stages is kind of like the operating costs. Solvent is kind of, I'm sorry, my mind is mush today as well. Stages is capital cost. Solvent is operating costs. And in many processes we've seen so far, operating costs are often much greater than the capital startup costs. So when you're designing these systems, you want to prioritize using less solvent with making a big initial investment. So more stages, less solvent is typically good. And this is why in industry, I think you'll see most frequently, countercurrent is a little bit better than cross current for many applications. All right, sorry about how jumbled that got at the end. That's all for today. Have a nice weekend, and I'll see you on Monday.